Every single second, somewhere on this planet, a child dies because of contaminated or inaccessible water. Every single day, 2 billion people turn on a tap connected to nothing reliable. Every single year, water scarcity costs the global economy an estimated $500 billion in lost agricultural productivity, industrial shutdown, and public health collapse. A number that the World Bank projects will reach 6% of GDP in water-stressed regions by 2050. And yet, the solution has been sitting in front of humanity for the entirety of recorded history, covering 71% of the Earth's surface, holding 1.335 billion cubic kilometers of water in a reservoir so vast it will never empty on any timescale relevant to human civilization. The ocean. The problem is not that the ocean lacks water. The problem is that every liter of seawater carries approximately 35 grams of dissolved salt, sodium chloride, magnesium sulfate, calcium carbonate, and dozens of other ionic compounds that make it physiologically toxic to drink, corrosive to infrastructure, and lethal to crops. Removing those 35 grams per liter from billions of liters per day is one of the most energy-intensive, technically demanding, and critically important engineering challenges of the 21st century. The answer is a pressure vessel the size of a torpedo, a membrane thinner than a human hair, and 60 to 70 bar of hydraulic force, 870 pounds per square inch, that drives water molecules through that membrane while leaving salt, bacteria, viruses, and every dissolved contaminant behind. This is reverse osmosis. And inside the world's mega desalination plants, from Saudi Arabia's Al-Khair facility producing 1.025 billion liters per day, to Israel's Sorek B plant treating water at 2.2 kilowatt-hours per cubic meter, to the emerging gigaplants of India and China, it is happening continuously, relentlessly, at a scale of industrial precision that most people living on its output have never seen and cannot imagine. Join QuitTech Process as we uncover the secrets behind this engineering marvel. The water economy. The economics of desalination have undergone a revolution so dramatic in the past 25 years that the technology has moved from the exclusive province of oil-rich Gulf states, the only economies that could afford its historically prohibitive energy costs, to the front line of water security strategy for nations as diverse as Israel, Australia, Singapore, Chile, India, and the United States. In 1995, the energy cost of producing 1 cubic meter of desalinated water by reverse osmosis was approximately 10 to 15 kilowatt-hours, making the process economically viable only where conventional freshwater was completely absent and energy was essentially free, as in the Gulf states burning their own petroleum to power their distillation plants. Today, the most efficient large-scale RO facilities in operation achieve specific energy consumption of 2.2 to 2.5 kilowatt-hours per cubic meter, an 80% reduction in energy intensity over 3 decades, achieved through advances in high-efficiency pump design, membrane permeability improvement, and critically, pressure energy recovery technology. The economic consequence of that efficiency improvement is transformative. At 2.2 kilowatt-hours per cubic meter, the energy cost of producing 1 cubic meter of desalinated drinking water, approximately 1,000 liters, is less than 20 US cents at average industrial electricity prices. The total production cost, including capital amortization, chemicals, membrane replacement, and operations, ranges from $0.50 to $0.80 per cubic meter in large modern facilities, competitive with the cost of delivering water from distant reservoirs through long pipeline systems in many parts of the world. The global desalination market reflects this economic transformation. In 2000, global installed desalination capacity was approximately 22 million cubic meters per day. By 2024, it exceeded 120 million cubic meters per day, a 5-fold increase in 24 years. The market is growing at 9% annually and is projected to reach 300 million cubic meters per day by 2040. Saudi Arabia, the United Arab Emirates, and Kuwait together account for 45% of current installed capacity, but the fastest growth is now occurring in India, China, California, and North Africa, driven not by petroleum wealth, but by the simple, unavoidable arithmetic of population growth and aquifer depletion. Israel provides the most compelling economic case study. A nation of 9.7 million people in an arid Mediterranean climate, Israel now obtains 85% of its domestic water supply from seawater desalination. 5 plants operating on the Mediterranean coast, producing a combined 800 million cubic meters per year. The plants resolved what had been an existential national water crisis. Israel's agricultural sector, which had been contracting for decades under water restrictions, has expanded. The national water deficit has been converted to a surplus. The cost of this transformation, approximately $2 billion in plant construction, has been returned many times over in agricultural productivity, industrial water availability, and the elimination of the GDP losses associated with water scarcity. Inside the membrane. The reverse osmosis process at the heart of a mega desalination plant is, in its physical principle, disarmingly simple. Apply sufficient pressure to salt water against a semi-permeable membrane, and the water molecules will pass through while the dissolved ions cannot. In its engineering implementation at industrial scale, it is anything but simple. It is a cascade of precisely controlled physical and chemical processes, each dependent on the one before it, each demanding tolerances that leave no room for error. Stage 1. Intake and screening. Every mega desalination plant begins at the ocean, either through open ocean intake structures positioned offshore at depths of 15 to 30 meters, or through beach well infiltration galleries where seawater percolates through the natural sand substrate before entering the plant. Open ocean intakes use velocity cap structures that limit approach velocity to 0.09 meters per second, slow enough that fish and marine organisms are not entrained. The intake water passes through 10mm bar screens and 1mm fine screens that remove macroscopic marine material, seaweed, jellyfish fragments, fish, debris before entering the pre-treatment system. At the world's largest plants, the intake flow rates are staggering. The Al-Khair facility in Saudi Arabia intakes 4 million cubic meters of seawater per day, 46 cubic meters per second through intake tunnels bored 40 meters below the seabed of the Arabian Gulf to protect against surface contamination. Israel's Sorek B facility draws 2.4 million cubic meters per day through a single offshore intake structure with a 2.8-meter diameter pipe extending 1.8 kilometers into the Mediterranean. Stage 2. Dissolved air flotation and coagulation. Raw seawater arriving at the treatment plant carries suspended solids, algae, dissolved organic matter, and biological content that would foul the RO membranes within hours if allowed to reach them. The first treatment stage applies coagulant chemicals, ferric sulfate or polyaluminum chloride at doses of 3 to 8 milligrams per liter that destabilize the colloidal particles and cause them to aggregate into larger flocks that can be removed mechanically. In dissolved air flotation, pressurized water supersaturated with air at 6 bar pressure is released into the coagulated flow, generating billions of microscopic air bubbles 10 to 100 microns in diameter that attach to the flock particles and carry them upward to form a floating sludge blanket at the water surface. The sludge is continuously scraped off by mechanical skimmers. The clarified water beneath is drawn off for the next treatment stage, with turbidity reduced from the raw seawater value of 5 to 50 NTU to below 1 NTU. Stage 3. Ultrafiltration, the guard before the gate. In the most advanced modern desalination plants, including the 560,000 cubic meter per day Hasyan facility in Dubai commissioned in 2024, the dissolved air flotation step is followed or replaced by hollow fiber ultrafiltration membranes, which provide a more consistent pre-treatment quality that extends RO membrane life and reduces chemical consumption. Ultrafiltration membranes are polyvinyl difluoride hollow fibers, each 1 to 2 millimeters in outer diameter with a wall thickness of 0.2 millimeters, bundled by the thousands into pressurized modules 2 meters long and 200 millimeters in diameter. The seawater is forced under 3 to 1 bar pressure through the fiber walls, and particles larger than 0.02 microns, bacteria, protozoa, suspended solids, colloidal matter, are physically excluded from passing through the membrane wall. The ultrafiltrate emerging from the fiber lumen side has a silt density index below 3, the internationally recognized threshold for RO feed water quality, regardless of how variable or biologically active the raw seawater has been. Stage 4, high-pressure pumping, building to 65 bar. The pre-treated seawater enters the high-pressure pumping system, the mechanical core of the RO process and the largest single energy consumer in the facility. High-pressure centrifugal pumps in up to 3 stages raise the feed water pressure from near atmospheric to 55 to 70 bar, depending on the seawater salinity and the required permeate recovery rate. At the Sorek B facility in Israel, the high-pressure pumps are 22 megawatt electric motor-driven centrifugal units, each the size of a small house, operating at 3,000 RPM and delivering 35,000 cubic meters per hour against 65 bar head in a single-stage impeller. It is at this pressure, 65 bar, approximately 65 times atmospheric pressure, that the physics of reverse osmosis become active. The osmotic pressure of standard seawater at 35,000 milligrams per liter total dissolved solids is approximately 27 bar. To drive water molecules across the membrane against this osmotic gradient requires a net driving pressure that exceeds 27 bar. At 65 bar applied pressure, the net driving pressure is approximately 38 bar, sufficient to force water through the membrane at an economically viable flux rate while maintaining acceptable membrane life. Stage 5, the pressure vessel, 7 membranes in series. The high-pressure seawater enters the pressure vessel arrays, the visual signature of every large RO facility, recognizable as rows upon rows of blue or gray cylindrical housings 300 millimeters in diameter and 6 to 7 meters long. Inside each pressure vessel, 7 spiral-round membrane elements are arranged in series. Each element is a sheet of thin-film composite polyamide membrane, a 3-layer structure comprising a 200 nanometer thick active polyamide layer, a polysulfone support layer 40 microns thick, and a polyester backing fabric wound around a central perforated collection tube with feed channel spacers separating the membrane envelopes. The active polyamide layer, 200 nanometers or 0.0002 millimeters thick, is where the desalination actually occurs. At 65 bar, water molecules migrate through this layer by a solution diffusion mechanism. They dissolve into the polymer matrix on the high-pressure feed side, diffuse through the dense polymer chain structure under the chemical potential gradient created by the pressure differential, and emerge on the low-pressure permeate side. Sodium and chloride ions, too large in their hydrated form and carrying electrical charges that the neutral polymer matrix repels, cannot follow this pathway. The result is a permeate water containing less than 300 milligrams per liter of total dissolved solids, down from the feed water's 35,000 milligrams per liter, a 99.1% salt rejection achieved in a membrane layer thinner than a bacterium. At the Al-Khair facility, 120,000 pressure vessels operate in parallel, containing 840,000 individual membrane elements. The total active membrane area is 31 million square meters, 31 square kilometers of polyamide film, all operating at 65 bar, all simultaneously separating water from salt 24 hours a day, 365 days a year. Stage 6, energy recovery. Capturing what would be lost. The brine stream rejected by the RO membranes, the 45 to 55% of feed water that does not permeate, exits the pressure vessels at 60 to 64 bar, having lost only 1 to 5 bar of pressure to friction. This high-pressure brine stream contains enormous quantities of hydraulic energy that in early RO systems was simply dissipated through pressure-reducing valves and lost as heat. In modern large facilities, this energy is recovered by isobaric pressure exchangers, rotary ceramic piston devices that transfer the pressure from the high-pressure brine directly to the incoming low-pressure seawater without any intermediate energy conversion. The pressure transfer efficiency exceeds 98%. The energy recovery devices at the Sorek B facility recover 32 megawatts of hydraulic power continuously, equivalent to removing 32 nuclear power plant-sized loads from the electrical supply. Stage 7, post-treatment, from ultra-pure to drinkable. They permeate water from the RO membranes while essentially free of salt, bacteria, and viruses, requires post-treatment before it is suitable for distribution. It is slightly acidic, pH 5.5 to 6.0, aggressive towards metal pipes, and completely devoid of the calcium and magnesium minerals that make water palatable and that protect distribution infrastructure from corrosion. Limestone remineralization contactors restore alkalinity and hardness. Carbon dioxide stripping removes the excess dissolved carbon dioxide, contributing to the low pH. Final disinfection with sodium hypochlorite at 0.5 milligrams per liter provides residual protection through the distribution network. The finished water meets WHO drinking water quality guidelines in every parameter. The steel giants of desalination. The machinery of a mega desalination plant operates at a scale that reframes what industrial engineering means. The high-pressure pumps at Israel's Sorek B facility are perhaps the most powerful single-stage water pumps ever built for a civilian water supply application. Each pump weighs 180 tons, measures 8 meters in length and 3 meters in diameter, and is driven by a 22-megawatt electric motor, an asynchronous so large that the facility has its own dedicated 161 kilovolt electrical substation serving the pump hall alone. The pump impeller diameter is 900 millimeters, rotating at 3,000 revolutions per minute, generating a tip velocity of 141 meters per second. At full operation, 6 of these steel giants operate in parallel, consuming 132 megawatts of electrical power, the output of a medium-sized power station, to maintain the 65 bar operating pressure across 120,000 pressure vessels simultaneously. The isobaric pressure exchanger units, manufactured by Energy Recovery Inc. of the United States under the brand name PX Pressure Exchanger, are marvels of rotary precision engineering. Each unit is a ceramic rotor 25 centimeters in diameter and 30 centimeters long, spinning at 1,200 revolutions per minute inside a ceramic sleeve with a clearance of 25 microns, a quarter of the diameter of a human hair. The ceramic rotor contains 12 cylindrical channels that alternately receive high-pressure brine and low-pressure feed water as the rotor turns, transferring pressure between the two streams with 98.5% efficiency and a leakage rate of less than 3% of the treated flow. The Al-Khair facility operates 2,400 of these units, a steel giant of an energy recovery system consuming an entire building and recovering 380 megawatts of hydraulic power continuously. The ultrafiltration pre-treatment system at Hasyan in Dubai is equally imposing in its scale. The UF building houses 45,000 individual hollow fiber membrane modules, each 2 meters long, 200 millimeters in diameter, containing 10,000 individual PVDF fibers. The modules are arranged in racks 12 meters high and 200 meters long, the combined fiber length in the building exceeding 900,000 kilometers, enough fiber to wrap around the Earth 22 times. Engineering against salt, heat, and biology. The mega desalination plants of the Arabian Gulf operate in an environment that tests every engineering system to its absolute limit. The Arabian Gulf is the saltiest large sea in the world, with average salinity of 43,000 to 45,000 milligrams per liter, 25% higher than open ocean seawater, due to the shallow and closed nature of the Gulf and the extreme evaporation rates in a climate where air temperatures routinely reach 50 degrees Celsius in summer. At 45,000 milligrams per liter salinity, the osmotic pressure of the feed water is 35 bar rather than the 27 bar of open ocean water, requiring operating pressures of 70 to 75 bar and increasing energy consumption by 25% relative to Atlantic or Pacific installations. The biological challenge is equally severe. The Arabian Gulf experiences intense seasonal algal blooms, including the toxic dinoflagellate Noctulica scintillans, which turns vast areas of the Gulf red during bloom events that can increase the organic loading of intake water by a factor of 200 within 48 hours. The 2008 Noctulica bloom forced the shutdown of multiple Gulf desalination facilities simultaneously, creating a water supply crisis that lasted weeks and drove emergency engineering investment in biofouling control systems. Modern Gulf facilities now carry pre-treatment systems designed for 300% of normal biological loading, with dissolved air flotation systems capable of handling raw water turbidities of 500 NTU without reducing output. In the Mediterranean, where Israel's coastal plants operate, the challenge shifts from heat and salinity to seismic risk and jellyfish. The Mediterranean basin is seismically active, and the pipelines and structures of coastal desalination facilities must be designed to withstand magnitude 7.0 earthquake events without structural failure. The giant jellyfish Rhizostoma pomo, which can reach 35 kilograms and moves in swarms of millions in the eastern Mediterranean, can block intake screens so rapidly that drum screen speed must be increased from 1 revolution per hour to 1 revolution per minute during swarm events, and chemical dosing systems must be activated within 10 minutes of swarm detection to prevent biofouling from progressing into the pre-treatment system. The rebirth of water civilization. There is a version of the 21st century in which the wars are fought not over oil or ideology, but over water, in which the depletion of the Ogallala aquifer collapses American grain production, in which the Indus River's glacial source disappears and 220 million Pakistanis face an existential water crisis, in which the cities of the American Southwest are abandoned to the desert that was always beneath them. And there is another version. In that other version, the engineering of reverse osmosis has continued its 30-year trajectory of improvement. Membrane permeability has doubled again, reducing operating pressure to 35 bar and energy consumption to 1.2 kilowatt-hours per cubic meter. Pressure exchangers approach thermodynamic perfection, recovering 99% of brine energy. Renewable energy, solar in the Gulf and North Africa, wind on coastlines, has driven the electricity cost to near zero during peak generation hours, making desalinated water not merely competitive with conventional supply, but demonstrably cheaper in water-stressed regions. In that version, the 200 nanometer polyamide layer, thinner than a bacterium, invisible to the naked eye, manufactured by the square kilometer in automated facilities in South Korea, Japan, and the United States, has become the foundation of civilizational water security for 3 billion people. Israel has already crossed that threshold. Singapore crossed it in 2005. Saudi Arabia crossed it in the 1970s and has been living beyond it ever since. Australia crossed it during the Millennium Drought and never looked back. The question is not whether reverse osmosis can provide the water that aquifers and rivers can no longer supply. The 21 square kilometers of membrane in the Ras Al-Khair facility answer that question definitively every second of every day at 65 bar without pause. The question is whether the rest of the world will build the plants in time. For more engineering marvels that are redefining what civilization can survive, subscribe to QuitTech Process. The secrets of the technology that will keep the 21st century livable are waiting, and we will uncover every single one of them.